Konnichiwa. Unfortunately, that's where the Japanese stops. What I'd like to do with this presentation is to talk about two really big new features in Java SE 8. Lambda expressions, which are a feature introduced into the syntax of the Java language. And the Streams API, which is a new part of the class libraries that makes extensive use of Lambda expressions. As an Oracle employee, first slide that I must put up is the safe harbor statement. This essentially says that we're not committing to deliver anything on a particular date. Since JDK 8 was launched about a year ago, I think we're fairly safe that we don't need to look at that for too long. Let's start with Lambda expressions and what they are and why we need them. This is a very common piece of code that we would use in Java. It uses an anonymous in a class. And these were introduced way back in JDK 1.1. And as we can see, what we want to do is we want to create a new thread. And we want to have some code execute in this thread. In order to do that, the thread constructor needs a class, an object, which implements the runnable interface. Now, we could do that by creating a separate class. We could then have that class implement the runnable interface, have a run method with the code, and use an instance of that class. But that requires a lot of extra work. So an anonymous in a class allows us to effectively say, create me a class and an object at this point. So the compiler will create an instance of a class which implements the runnable interface. And then by defining that we have a run method which has some code to execute, when we create the thread, an object will be passed as a parameter, and then we can start the thread. So this works. This is fine. But it has some big drawbacks. There's a lot of extra code there, a lot of what's commonly referred to as boilerplate code. So we have to say new runnable. We have brackets. We have to define that the method is called run. But if you think about it, the compiler will know that already because the thread constructor has a version which takes a runnable as a parameter. So a Lambda expression allows us to simplify this. What we end up with is a piece of code like this. So now, rather than having to actually create this new runnable and define the run method, effectively what we're doing is providing a definition just of the run method. And in that sense, we're just providing the code which is executed in that method. So you can see that run takes no arguments. So the left-hand side here, we have empty brackets, no arguments. We have an arrow to indicate that this is a Lambda expression. And then we have the body of the method to execute the code that we want to execute. So it really is a much simpler way of doing the same thing that we can already do with anonymous inner classes. Let's look at a little bit more detail of what Lambda expressions are and how they work. Now, I said that what you're effectively doing is creating a definition of a method. But we don't want to call it a method. We want to call it an anonymous function. The reason for that is that in Java, any method must be associated with a class. So this is object-oriented technology. A Lambda expression does not have a class associated with it. So it is different in that respect to how it is implemented compared to an anonymous inner class. But from the point of view of what you have there and its structure, it is the same as a method. So a method has a set of typed parameters. Lambda expression has the same. A method has a body, the code to be executed in that method. Same with the Lambda expression. A method has a return type, even if it's void. Same for a Lambda expression. And methods can throw exceptions. And we can do that with Lambda expressions as well. So structurally, they are exactly the same as a method, but because they're not associated with a class, we don't call them a method. We call them anonymous functions. The really big thing, the big advantage of this, is that it gives us a really simple way now of having not just parameters which are values that we can pass into methods or to assign to variables, but it also gives us the ability to define behavior that we can pass as a method to a method or assign to a variable. And if we look at this example code here, what I'm doing is taking a collection of students, and then I want to process that. And the methods that I use to process that collection tell me what it is that I actually want to do. So we can see that we want to take this collection of students and we want to filter it. So we want to provide a subset of that data. We then want to take that subset of the data and map from the student objects that we have to some particular value associated with those students. And then finally, we want to take that and we want to reduce it. This is the classic filter, map, reduce approach. In this case, what we're doing is using a special form of reduction, which is to find the maximum value. So these three methods give us what we want to do: filter, map, maximum value. The Lambda expressions that we pass as parameters to two of those methods tell the system how we want to use those methods. So in the case of the filter, we want to get all of the students who graduated in 2011. In the case of the map, we want to extract the score that those students got in their exams when they took them. I could very easily change this code, keep the filter, keep the map, and keep the max, but change the behavior. So by using a different set of Lambda expressions, I could extract, rather than students who graduated in 2011, maybe I want to extract students who were in Tokyo. And then, rather than getting the score, maybe I want to find the year that they were born, so I can find out how old they were. So you see how we can change the way the code works, not by changing the set of methods, but by changing the Lambda expressions. Now, one of the things about Lambda expressions is that they're not associated with a class. So what is the type of a Lambda expression? This is where things get a little bit more complicated. So when we deal with Lambda expressions, what we're actually dealing with is what are called functional interfaces. Now, a functional interface is one that has one abstract method. There's lots of examples of these types of interface in Java that we've been using before JDK 8. Things like runnable that we've already seen has a single method, run. Things like action listener has a single method, action performed, and so on. What's really nice about that is that wherever we have a functional interface reference, whether it's a parameter in a method or a variable that we're assigning a value to, we can use a Lambda expression. So we can use Lambda expressions for runnables, for action listener, for comparator, and so on. What the Lambda expression effectively does is, as we've already seen, provide the implementation of that single abstract method. So the Lambda itself doesn't have a type, but it is used where the type is a functional interface. And that way, where it's used will have a type representation. Local variables and their capture. When you use anonymous inner classes and you want to reference a variable from outside of that inner class, you have a restriction. The variables must be marked final, which means their value is set once and cannot be changed. With a Lambda expression, we still have the same restriction. And the reason for this is that in Java, we have closures on values, not closures on variables. Other languages, like Scala, for example, allows you to modify the state of a variable from outside the closure. So that's a closure on a variable. In the case of Java, we have closures on values, which means you can't change the state of a variable in the surrounding scope. This makes a lot of sense because if you want to use Lambda expressions in a multi-threaded environment, this prevents you from having problems with having different threads updating the same variable without the necessary locking. What we've done with Lambda expressions is to relax the rule a little bit. Now, if you want to use a variable from the surrounding scope, you can do so, but it must behave as if it was final. It doesn't have to be marked as final, but its value must be set once and it mustn't be changed. So in my example here, I'm passing a value called before into my method. And then in my Lambda expression, I'm testing against that value. So this is acceptable because before is only set once in this context and not modified. So it is effectively final. What does this mean for Lambda expressions? Now, this is where things are a little bit different to anonymous inner classes. Because with an anonymous inner class, the compiler is generating a class for you. And then when you use it, the runtime instantiates an object of that type. In an anonymous inner class, when you refer to this, you are referring to the instance of that anonymous inner class. But remember, Lambda expressions do not have a class associated with them. So there is no object to refer to with this. In the case of a Lambda expression, if you use this, you're actually referring to the object of the surrounding scope. And we'll see an example of this later on. Type inference. One of the things that we spent quite a lot of time doing in JDK 8 was to rewrite a large part of the compiler and how it handled inferring, determining the types of things where it wasn't explicit. Now, this has actually had some interesting impact because we now have a better way of doing this. Some code that would compile in JDK 7 actually gives you warning messages because the compiler is being more precise about how it interprets types. With a Lambda expression, and this was the reason for doing the rewrite, it allows us to be more flexible. Here's an example. I have a method that I'm defining, and I'm going to use a generic type parameter, t. This sort method is going to take two parameters. First is a list of type t, and the second is a comparator of type t or a superclass of t. So if we use this, here's an example. I want to take my list and get it from somewhere, and this is going to be a list of type string. Then I want to use my sort method. So I will pass the list as the first parameter. And then, because comparator is a functional interface, I can use a Lambda expression. The compare method takes two arguments, in this case string x and string y, and the body of the Lambda expression returns the difference in lengths. So we will sort them by length. But the thing is now that the compiler understands more about the types involved. So it knows more about what t really is. And this allows us to relax the rules about what you need to put in your Lambda expression. The compiler knows that list is of type string. So the comparator must also be of type string. And in this case, we can simply say x, y, to indicate the two values of the compare method, and again, return the length. But we don't need to explicitly state that these are of type string, because the compiler will work that out for us because of where we're using that comparator. Don't be too worried about this. We're not sneaking dynamic typing into Java. Java is still very much a strongly typed, statically typed language. And what we're actually doing is giving you more typing with less typing. And that's one of those jokes that doesn't really translate into Japanese, I don't think. Method references. This is another shortcut that we've provided. Very frequently, you end up with Lambda expressions like this, where you have a single argument, in this case a file f, and all the body of the Lambda expression does is to call a method on that argument. So rather than having you write all of that code, I know it's a lot shorter than it used to be, but it's still longer than we want, we have the idea of a method reference. So we can replace that Lambda expression with file : can read. And all that means is that it's the same as the Lambda expression above. So wherever you use that, it will generate the same Lambda expression and the same implementation. Because a constructor is in essence a method, we can do the same thing with a constructor. If I want to create the ability to have a new array list, then I can simply say array list : new. And that will return a Lambda expression that creates a new array list. So that's a quick introduction to Lambda expressions. Now let's talk about how we go about using Lambda expressions to make life easier in our Java code. I talked earlier on about how we could use filter, map, and reduce, the well-understood kind of algorithms. So we could do something like this. We can take our collection of blocks, filter them by color, map them to weight, reduce them to a maximum. Great. But there's a bit of a problem with that, which is the collection API doesn't have filter, map, and reduce in it prior to JDK 8. How do we go about adding those methods to the collections API? Well, in many cases, if it was just a class, it would be very straightforward. So we could just add new methods and we could use them. But the collections API uses a lot of interfaces. So collection is an interface. List set, map are all interfaces. What we need to do is add new methods to an existing interface. How do we do that? Well, again, we can modify the code, we can add new methods into the interface. But that's more problematic because if somebody's created their own implementation of list and they've compiled it and they've given it to you, then you come along and you say, I want to use filter, map, reduce on your list. So the compiler goes filter, okay, cross to your list and tries to resolve that method. But because this is compiled with earlier versions of Java, there is no filter method, there is no map method, there is no reduce method. The compiler will then have to stop because it can't resolve the method. So we need a way where we can add methods to an existing interface, but without breaking backwards compatibility. The answer to this is default methods. What we can now do is add a new method to our existing interface. So in the case of collection, we're going to add a stream method. Now what happens is that when the compiler tries to compile against an old collection, which doesn't have stream in it, it won't be able to resolve that method. But rather than just saying, I can't resolve it, I have to stop, it goes back to the interface and looks to see if there is a default implementation. If there is, what it actually does is to resolve that method by using the body here in terms of returning stream support.stream of splitterator. So it allows us to add methods without breaking backwards compatibility so that you can still compile against older code. Now, a lot of people go, well, hang on, just a minute. Aren't you now adding multiple inheritance to Java? You've always said multiple inheritance is a bad thing. Well, the answer is yes and no. Java already has multiple inheritance of types. If I create a new class, I can inherit from one other class. So that's single inheritance. But I can also implement any number of interfaces. And through polymorphism, when I view an object of that type, I can view it either as the class itself, any of its superclasses, but also any of the interfaces, which gives us multiple inheritance of types in Java. By adding default methods to interfaces in Java, what we've now done is provide multiple inheritance of behavior. So you can have behavior coming from a class, or you can have behavior coming from an interface. What we haven't done is to provide multiple inheritance of state. And this is very much where, if you look at languages like C++, where multiple inheritance causes you more problems. Now, that said, there are some things you need to be aware of when using default methods. For example, let's say I have a class which implements two interfaces, A and B. And both of those interfaces have a default method called find with the same signature. The class I create doesn't have find in it. So when somebody tries to use find from that code, the compiler has to go to the interfaces and say, interface A has a find method. Interface B has a find method. And it's then presented with a problem. Which implementation should it use? First one? Last one? Pick one at random? The answer is that if it cannot resolve between two identical implementations, then it will report an error. At which point, you would need to go in and modify your code and have it use either the implementation in A or the implementation in B. Another thing we did in JDK 8, because we now allow behavior in an interface, we also allow you to put static methods in an interface. So there's behavior in those as well. Having said all that, let's go back to functional interfaces. We looked at some examples earlier on, runnable, action listener, and so on. And I said that a functional interface was one that had a single abstract method. Now in JDK 7, that was easy, because any interface that had one method was going to be a functional interface. In JDK 8, it's a little bit more complicated. Predicate is a new interface that's part of the function package that we're going to see in a few minutes. Predicate is a functional interface. It has one abstract method. But if you look at the code, it actually has 5 methods. The reason for that is that 3 of those methods have default implementations. By definition, if you have an implementation, it's not abstract. The other method is a static method. Again, static method has an implementation, so it's not abstract. So predicate, despite having 5 methods, only one of them is abstract, and therefore it is still a functional interface. If you want to create your own functional interface, you can do that, and you can tell the compiler that you think it is functional. So you can use the annotation functional interface, and the compiler will check for you that you have obeyed the rules. So we've talked about Lambda expressions, and now we've talked about how we can extend the collections APIs, interfaces, through the use of default methods. Let's see how we bring those two things together to create the Streams API and see what you can do with it. So what is a stream? Well, at a high level, you can think of it as being like an aggregate computation. So how do you process a set of data? We've seen examples where we take a collection, we want to do something with it. So that's what we're dealing with. Now, the important thing about a stream is to understand that it's not a new data structure. It often looks like a data structure, but it's not. The other thing that's a little odd about streams is that you can have infinite streams. And this sometimes confuses people a little bit, because if we write code in Java, we can write an infinite loop very easily. While true, do something. And we use that because we don't know at what point we want to exit the loop. Within the loop, we have an if statement. We say, if some condition, break. And it drops us out of the loop. With a stream, you can't do that as such. There's no loop to break out of. So people think, infinite stream, how do I stop an infinite stream? The answer is that you can specify certain things. Like you can say, find the first element in that stream which matches some value. And that way, even if it's an infinite stream, once you get to that value, it will stop. What a stream allows us to do is to optimize how the code works internally. So we describe what it is we want to do with the methods. We describe how we want to do it with the Lambda expressions. But we don't actually specify the details of how all that happens underneath. The library code does that for us. This enables us to use things like lazy evaluation. It allows us to do parallel operations without you having to write extra code. And we'll see some examples of these in a moment. Now, in terms of what a stream is, you can think of it like a pipeline. A pipeline has two ends. passing something from one place to another. At one end, you have a stream source. A stream source is what you create from a collection of data, and that's what you want to process. You take that stream, and then you pass it through 0 or more intermediate operations. An intermediate operation is one that takes as input a stream and then generates as output a stream. That way, you can connect the output of one intermediate operation to the input of another one. And you can do that as many times as you like. Once you've done all the intermediate processing, you need the other end of your pipeline. You need some result to come out, or you need something to happen. And for that, you have a terminal operation. Terminal operation is one that takes as input a stream, but doesn't generate as output a stream. It may generate a value, it may generate a collection, it may just print something, but it terminates the stream. So here we have another example. I have a collection of transactions, and what I want to do is process that. So I create a stream source using the stream method. I pass that stream into an intermediate operation, filter. And again, I use a Lambda expression to say that the objects that I want to extract from that collection are all the ones where the buyer has a city that's London. I then pass that stream, which is a subset of the original data, into map to int. And that's another intermediate operation. Here, we use the method reference to say that we want to get the prices of those transactions. And then we pass that stream into a terminal operation, which is to sum all of the results in the stream. So we add them all up and give a total. There's one other thing to mention here, which is the fact that I've used map to int rather than just map. Java is a little bit strange as a language because it's not really truly object-oriented. We deal with objects a lot, but we also have primitives. We have int, float, double, and so on. If we use map in this situation, we have to deal with objects. So we take the transactions, and then we map them to the value of that transaction. But we have to create an object. So we create an integer object with the int value inside it. That's auto-boxing. When we want to sum that, we have to go the other way. So we have to take all those objects, extract the primitive value from it, and add them all up. That's a lot of extra work. If I use map to int, what I'm actually creating is a stream of primitives rather than a stream of objects. So it makes sure that the overhead of creating objects and then using the values from those objects is eliminated. Where can you get streams from? Well, obviously collection has stream as a method. So that will return you a stream from a collection. And that's a sequential or serial stream. There's also another method called parallel stream. And that will return a stream which will be processed in parallel. The way the code works in the library is to use the fork join framework that was introduced in JDK 7. It splits up the job into a number of subtasks, hands them off to different threads, and has them execute in parallel. If you have an array, you can create a stream from that because it's really just a collection of data. So you can use arrays.stream. If you want to generate an array, a collection, you can do stream.of and specify how to create that stream. There's some useful static factories things like files.walk. You can specify the path of the point in your file system, and what you get back is a stream of the files and directories below that, which makes it easy to process file system relevant data. Now, terminal operations. One of the things I've talked about is the fact that we take the source of our stream and we pass that to an intermediate operation. We then pass the results of that as a stream to the next operation and so on until we get to a terminal operation. But that's actually not the way that it works, because if we did it that way, it would be very inefficient in certain situations. If we had, let's say, 1,000 elements in our collection, and we wanted to find the first element which matched a certain criteria, and we had to go through filter and map first. What we don't want to do is take all 1,000 elements, process it through filter, take all the elements that are returned by the filter, pass those through map, and then pass that set of data to find first. Because if the first element in that collection matches our criteria, we really only want to process one element, and that's what happens. So we effectively pull each element through the stream as we need it. So it gets passed through filter to see if it's actually matching our criteria, then it gets mapped into whatever value, then it gets passed to find first. So if the first element matches, we stop. We don't process any more data. There are a number of other optimizations that we can apply in our library code to allow things to run as effectively as possible. And there are various characteristics that we store associated with streams to make sure that we can do that as efficiently as possible. Now, I've used map in a couple of the examples, but we also have a thing called flat map. A map is, in essence, like a mathematical function where you have a one-to-one mapping. Each element on the input stream creates one element on the output stream. So that's easy. Sometimes, though, what we want to do is to have each element on the input stream create its own stream of results. And then what we want to do is to pass that as a set of results to the next part of our stream. But what we end up with is a stream of streams. So we don't want that. So flat map will take a situation where you have a one-to-many mapping. Each element on the input stream can potentially create multiple elements for the output stream. And we concatenate or flatten those into a single output stream. And we'll see an example of that in a moment. It makes it clearer what that is. Now, there's another class that was added to JDK8 called the optional class. And this is used a lot in the Streams API. But it's not just for the Streams API. It can be used in many other places as well, but it is very useful. And it's all about how to eliminate problems with null references and to try and eliminate as far as possible null pointer exceptions. If you look at things like min and max, if there's no data on the input stream, what do we return as the minimum or the maximum value? We could say 0, but that doesn't really make a lot of sense. So we would return a null. So the problem is that we then have to test whether what we're getting back is null or not. Using an optional, what we get back is a guaranteed object. So we know that we're not getting a null. The optional holds a reference to some other object. So it's like a little container for an object. And that object could either be a valid reference or it could be a null. And then we can treat it in the same way as we do a stream of 0 or 1 elements. That way we can have things like if present, which will allow us to do something if there's a valid reference, or else, which will do something if there's a null reference. And we can be more complex. We can actually do things like mapping and filtering. You can even do flat map on an optional, which allows you to manipulate the data and do some very useful and interesting things. So let's look at some examples of using the Streams API and Lambda expressions and how we can build up some very powerful things. So the first example is I have a collection of words and I want to convert them all to uppercase. So that's straightforward. I take my collection of words, word list, and I create a stream source, stream. And then I map that using a Lambda expression, which in this case is a method reference, to say convert to uppercase. I pass that stream into a terminal operation called collect. And collect will gather all of the data from the input stream and store it in a collection. And we can define how that collection is created using one of the utility methods that we provided, such as collectors.toList. So it will take the results of the input stream, put them all in a list, and return that as your result. So that's good. What we could also do, though, is we could say, rather than that being a stream, serial stream, let's make it parallel stream. So now you see how easy it is to change the way the stream works from a performance perspective, not just a behavior perspective. A lot of the time when people look at that, they go, ooh, right, everything I do is going to be parallel. I'm going to use all those processors and all those cores that I have in my machine. Don't. The reason I say that is because if you look at what a parallel stream does, remember it uses the fork join framework, it will always result in more work than a serial stream. But if you have a large enough data set and enough processors and cores, it may finish quicker. But if you've only got 100 elements in your list, there's no point in doing it in parallel, because the overhead of creating the fork join framework, all the threads, the queues, and so on, far outweighs how quickly you can do the processing of 100 elements sequentially. So you need to think carefully about whether to make a stream parallel or not. Let's look at another example. Here, we want to count the number of lines in a file. And another method that we've added in JDK8 is very useful. So there's now a method in buffered reader called lines. What that will do is return you a stream of the lines from that reader. Assuming that you connect that buffered reader to a file, you get the lines of text from the file. Very simple. And then you can simply take that stream source, no need for any intermediate operations, pass it directly to a terminal operation, count. And it will count how many elements there are in the stream. And it will give you the number of lines in the file. Let's make things a little bit more complicated. How about if I want to take the third and the fourth line from a file and join them together? Well, I can take my lines as my stream source, then I can pass it into skip. And skip will skip past the first however many elements of the input stream and return it as the output stream. I can pass that to limit. And limit does the opposite. So it only returns the first however many elements of the input stream as the output stream. And then we can pass that into collect again, but use a different collector, in this case joining, which will join the results together. Now this is a good example of where we don't create streams for everything. So what we don't, let's say there's 1,000 lines in our file. We don't read all 1,000 lines. Pass that into skip, which returns 998 lines. pass that into limit, which returns 2 lines. What we actually do is we're smart enough to say, read the first 4 lines of the file, and we're done. Flat map. So this is where we do a one-to-many mapping. So let's say we want to take all the words in a file and collect them into a list. So now we use flat map. And we'll use a lambda expression where the parameter is line, so that's the line being read from the file. And we'll use stream.of to create a new stream, where we'll split the line based on some regular expression. And that will create a stream of the words. But each line probably has more than one word in it. So we flatten that out into a single stream of words. Pass that into filter to eliminate any 0-length words, in case we had 2 spaces or a space and a tab, and then collect it into a list. So you're starting to see the power of this now. Let's go crazy. What we do now is we want to create a list of unique words in lowercase sorted by length. So same approach as before. We use lines. We use the flat map to create the stream of words by splitting up the lines from the file. Eliminate the 0-length words. Then pass that into map, where we map all of the words into lowercase. Pass that into distinct, which will eliminate any duplicates. Pass that into sorted, and we'll use the same lambda expression we saw before, where we sort by length. And then pass that into collect, to collect it into a list. Now the great thing about this example is that it shows you the power of lambdas and the Streams API. Because if you try to write that in JDK7, you're going to end up with a lot of code. Now, when you first look at this, if you haven't used lambdas and streams, it looks kind of strange. But you very quickly get used to understanding how lambdas and streams work. And it very quickly becomes clear what the code is actually doing. So that's another really good thing about using this kind of thing, is it makes the code easier to understand. So just to conclude, Java really needed lambda expressions, lambda statements, because if we were going to change the libraries to take advantage of potentially parallel execution, we couldn't just do it by adding more APIs. We also needed a change in the language. What we then had to do was to add default methods, so we could extend the collections APIs built on interfaces without breaking backwards compatibility. And then bringing those 2 things together, we were able to create the collections, use the collections API and create the Streams API on top of that, so that we could do all these wonderful things in terms of processing data. So Java SE 8 actually evolved all of the parts of Java, the language, the libraries, and the virtual machine. And we will continue to do this in Java 9 and Java 10 as we continue to develop Java further. So with that, domo arigato.